Now we turn to the Fenwick tree. It keeps queries fast, but it also makes updates fast, so the data can change as often as you like. A prefix sum answers a query in big O of 1, but one changed element forces a full big O of n rebuild. Real programs mix reads and writes. Think of a live leaderboard or running sensor totals. The numbers keep changing. So we need a structure where both the update and the query are fast. A Fenwick tree, also called a binary index tree, does this. Each index is responsible for a small, overlapping range of elements. So changing one element updates only big O of log and stored sums, not all of them. Before the code, one rule about indexing. It trips up almost everyone. A Fenwick tree counts from 1 inside, not from 0. Your array is 0 indexed, positions 0 to n-1. But the Fenwick array bit uses positions 1 to n position I and bit matches at index I-1. Every update and query below takes a 1 index position. Mixing this up with a 0 indexed value is one of the most common Fenwick bugs. Now the Fenwick update. When one element changes, we do not touch every later slot. We jump. Each row of this table is one jump. Say we update position 6. We start at I equals 6. Its lowest set bit is 2, the smallest power of 2 inside 6. So bit at 6 is one of the slots we change. To find the next slot, we add the lowest set bit. 6 plus 2 is 8. Now I is 8. Its lowest set bit is 8, so we change bit at 8 too. Then 8 plus 8 is 16, which is past n8, so we stop. The update touched only 2 slots, bit at 6 and bit at 8. Why add the lowest set bit? Adding it moves to the next slot whose range contains the old index. So an update visits only the slots whose range covers the changed element. Predict first. We update index 5 adding 1. Which bit indices does that plus 1 ripple to in order following the low bit jump? Pause and trace it. Here is the answer. 5, then 5 plus low bit of 5, which is 5 plus 1, so 6. Then 6 plus low bit of 6, which is 6 plus 2, so 8. Then 8 plus low bit of 8 is 16, which is past n equals 8, so we stop. 3 indices touch, 5, 6, and 8. Never all the later indices. Only the big O of log n that actually cover position 5. Now the same idea as pseudocode, so it stands on its own without any language. The procedure is Fenwick update. It takes the array bit, its size n, a 1 indexed position I, and the change delta. While I is at most n, it adds delta to bit at I, then it moves I forward by I and negative I, the lowest set bit. That is the jump to the next responsible index. Why does I and negative I give the lowest set bit? To negate I, you flip every bit, then add 1. The add 1 carries up through the low 0 bits and stops at the lowest set bit, so that bit stays set while every bit above it flips. The and then keeps only that one shared bit, the lowest set bit. The C version maps 1-to-1 onto the pseudocode. The function is fenUpdate. It takes the bit array, a 1 indexed position I, and the change delta. The loop runs while I is at most n. After each pass it does I plus equals I and negative I. That adds the lowest set bit and jumps to the next responsible index. The body is one line. It adds delta to bit at I. The update costs big O of log, and there are at most floor of log base 2 of n, plus 1, iterations, because each jump moves the lowest set bit to a higher position. This is the main operation of the chapter, shown at 3 levels of precision. The table reads left to right, from the idea to pseudocode to C. First row, the change itself. The concept is add delta at index I. The pseudocode writes bit at I equals bit at I plus delta. The C writes bit at I plus equals delta. Same thing, 3 ways. Second row, the jump. The concept is jump to the next covering index. Both the pseudocode and the C add I and negative I, the lowest set bit. Third row, the stop. We keep going while I is at most in, and stop once I passes the end of the array. Notice something. We need no memory trace here. A Fenwick tree is a plain array, not a pointer structure. There are no addresses and no arrows, just index arithmetic. That is the theme of this whole chapter, arithmetic instead of pointers. The update jumps upward. The prefix query jumps the other way, downward. A prefix query asks for the sum of the first I elements. Each row of this table is one jump. Say we want the sum of the first 6 elements. We start at I equals 6. We read bit at 6, which is 9, and add it to a running sum, giving 9. Then we subtract the lowest set bit 2, so I becomes 4. Now I is 4. We read bit at 4, which is 10, and add it, giving 19. Then we subtract its lowest set bit 4, and I becomes 0, so we stop. The answer is 19. Notice the pattern. Updates and queries use the same low bit jump, just in opposite directions and along different chains. An update at 6 climbs to 8. A query at 6 descends to 4, then 0. Both take big O of log and steps. Here is the prefix query in pseudocode. It takes the bit array and a 1-indexed count I sum starts at 0. Then, while I is greater than 0, we add bit at I into the sum and jump to the previous covering index by subtracting I and minus I. Notice the direction. Update adds the low bit and climbs. Query subtracts it and descends. Same jumps, opposite way. And here it is in C. Fen prefix query takes the bit array and a 1-index I. Sum starts at 0. The loop runs while I is greater than 0, and each step drops the low bit, which is I minus equals I and minus I, adding bit at I as it goes. The cost is big O of log n, the same low bit jump as the update, just subtracting instead of adding. It walks a different chain, but still at most log n steps. A Fenwick tree answers prefix sums directly. It sums the array from the start up to some index, but often you want the sum of a middle range. From L to R, this function does that. It takes the tree called bit and the two ends L and R. The trick is one subtraction. The sum from L to R is the prefix sum up to R plus 1. Minus the prefix sum up to L, you take the whole block from the start. Then remove the part before L. This is the same subtraction trick as the plain prefix array. One special case comes first. If L is equal to 0, there is nothing to remove. So we just return the prefix sum up to R plus 1 with no subtraction. Each prefix query is big, O of log n. We do 2 of them, so a range sum is still big, O of log n overall. And unlike the static prefix array, this structure also supports fast updates. Let's run the Fenwick tree. We start with an array of 8 numbers: 3, 2, minus 1, 6, 5, 4, minus 3, 3. First, we build the tree. This loop walks each element and calls fen update once per element, inserting them one at a time. The bit array holds the tree. Then we ask 2 questions. We print the prefix query of 6 and the range sum of 2 to 5. Next, we change one element. We call fen update to add 10 to bit position 3, which is at index 2. Then we print the range sum of 2 to 5 again to see the change. Look at the output. The prefix query of 6 is 19. That is the sum of the first 6 elements. The range sum of 2 to 5 is 14. After the update, the prefix query of 6 jumps to 29. That is the old 19 plus the 10 we added. And the range sum of 2 to 5 is now 24, 10 more than before. Notice the cost of that one change. A plain prefix array would need a full big O of n rebuild. The Fenwick tree touched only 3 entries, 3, 4, and 8.